All right. So we're just going to do a sample lab type question here. I managed to ask basically every lab's skill that we typically see on the free response. So some parts might seem a bit repetitive, but this is just to show kind of all the variations of question you could be asked without changing the context here. So this whole lab is going to revolve around this lovely spherical object right here. Called the Wisusic Super Ball. So suppose a group of students are playing with the hottest new toy on the market, the Wisusic Super Ball, of course. The toy is a squishy sphere that can easily roll, but the students cannot determine how its mass is distributed within the sphere. So anytime we're talking about how mass is distributed, that is 100% going to relate to moment of inertia. Because an object's resistance to change how it's rotating, that's entirely dependent on how that mass distribution is. Because again, it's hardest to get things rolling that have mass very far away. It's like the hoop versus the disc. So first, we have a design task here. Suppose students simply want to test if the ball is hollow or not. Develop a simple procedure that the students can perform to test whether the ball is hollow. And it says here we have to describe an experiment requiring no calculations that the students could perform to test if the ball is hollow or not. We should include a sketch of our setup, including any additional materials we need. And after that, we're going to identify what results of the experiment would verify/refute whether the ball is hollow. So we're saying, what can we do that doesn't require any computation, but can still tell us whether this ball is hollow or not? Well, the key to this is going to use that idea of the moment of inertia shape race. So if you put a bunch of objects on top of a ramp and race them, the objects with the lowest shape constant will finish first. So what that means is that if we take a hollow sphere to be our test object, something we know for sure is hollow, we can even construct one if we want, and we take that object, the Wisusic Super Ball, and the ramp, well, if we race those two objects down the ramp, the result of that race will tell us how the mass is distributed inside the Super Ball. Because it's also a known fact that things like mass and radius don't matter, it's entirely based on the shape, assuming it's actually rolling. So, the object that wins the race will have the lower shape constant for the moment of inertia. If the objects finish at approximately the same time, that means they're roughly the same shape, meaning the ball is hollow. But if your test object actually loses the race to the Super Ball, well, that means that the Super Ball must have its mass not concentrated all the way at the wall, so it must mean that its mass isn't all at the boundary. So we're really just interested in seeing the result of this race. So now, after a series of experiments, the students determine that the ball is neither completely solid nor completely hollow. For their next experiment, the students wish to quantitatively determine the toy's moment of inertia. Outline an experiment the students can perform to determine the moment of inertia of the Super Ball. Assume that all standard physics laboratory equipment is available. So we're going to draw a diagram. We're going to label each quantity to be measured and what tools should be used to collect each measurement. Okay, well, if I'm thinking moment of inertia, I should be thinking torque, rotation, all of those things. But the fact this is a sphere tells me that this thing is going to be nice and well behaved if we decide to roll it. So we're actually going to bring out the ramp again, and we're going to bring out the Super Ball again. And all we need to do is set up some sort of energy conservation equation. Because again, what I suggest to start with whenever you're trying to actually design a lab is write some sort of equation that contains the quantity of interest here. So we know that by energy conservation, if I put this object on a ramp, So if I put the ball on top of a ramp, and we'll give it a height too. That I don't need an arrow. We'll just do this. So if the ball initially starts a distance h above the ground, we can set up the energy conservation equation that we know that the mgh at the start gets turned into two forms of kinetic energy because the ball is translating at the bottom, but since it's rolling, it's also rotating at the bottom. And I see that I mixed my m's again, so let's just fix that here. I'll fix my mgh. So notice that in order to determine this moment of inertia, I basically got to get everything else out of this. So I need m, I need g, which is a constant, I need h, which I can measure, and I need v. And notice I also actually need omega, but that's not actually a different thing because omega is equal to v divided by r. So I guess I also do need the moment of the radius of the sphere. So we got basically four things to measure here. So we got to record the height h, and maybe I'll actually color code these values here. We need the height h. We need the mass m of the sphere, which we can easily get from the scale. We need the radius of the sphere, which we can easily measure. And then we got to get v. So v, we could get cleverly via kinematics, but again, we're saying that we got all the physics equipment here. So all we're going to do is at the bottom of the ramp, we're just going to put a little photo gate at the finish line. And we're going to measure v from the actual photo gate. And we'll label this as a photo gate. So that's it. So we can get m from a scale, of course. We can get h and r from a meter stick or ruler. And we can get v at the bottom of the incline just from a photo gate. So measuring all those things and letting our ball roll to the bottom, it'll spit out the speed. So describe the procedure we do with this. Clearly identify steps taken to reduce uncertainty. Well, I'm just putting into text basically what we just said here. Measure the mass in kilograms and radius of the ball in meters. Choose a set height, h, that we're going to drop the ball from every time. Record the velocity of the center of mass at the bottom of the incline after it rolls. Repeat for the same h multiple trials and take an average VCM to reduce experimental uncertainty. Because again, if we drop it from the same height, just taking multiple measurements is going to get us a better estimate of what the true value of V is for that h. And then you just set up a energy conservation equation to solve for I. And notice we have everything we need to solve for I. So that would be a complete design your own. So next we'll move on to the variant of here's the lab they did, and I used the one we just made for inspiration here. And we actually have to analyze it and do the data part for that. So finally, the students wish to calculate the shape constant for the super ball. The shape constant is a coefficient beta such that I is equal to that constant times mr squared. It's the number in front of the mr squared is how I like to think about it. Again, it's 1 for a hoop, 1/2 for a disc, 2/3 for a hollow sphere, and so on. We're interested in what that value is. So, common theme with the lab question is that they'll actually tell you the end result with the formula and have you derive it so that you can still analyze it even if you get stumped on the physics here. So, from our experiment that we did earlier, we want to show that the velocity at the bottom is just given by this expression, square root 2gh over 1 plus shape constant. So we are going to start from the same equation we had earlier, where we know that the potential energy at the top is equal to the kinetic energy at the bottom. But again, we are rotating here. So we know this is mgh, obviously, but kinetic energy at the bottom has two terms here. The translational kinetic and the rotational kinetic. And I see that I keep calling this capital M when it should be lowercase. Okay. Now we use the fact that it rolls without slipping. So again, this is a pretty standard calculation here. So if it rolls without slipping, that means that we can make the nice replacement that omega is equal to V over R, which means that omega squared is just going to be V squared over R squared. And then we can also use our expression for the moment of inertia of this thing in terms of shape constant. Because we were also given that the moment of inertia of this object is equal to some magic shape constant beta times mr squared. So we can just write the moment of inertia as beta times mr squared, and then we still got our omega as v squared over r squared. And notice that the r's cancel, and I keep making this m capital, and I really shouldn't. But the m now cancels from everybody. And we get gh is equal to 1/2 VCM squared plus 1/2 times beta times VCM squared. So multiplying both sides by 2, we get 2gh is equal to VCM squared times quantity 1 plus beta, which means that VCM quantity squared is equal to 2gh divided by 1 plus beta, which means that the velocity of the center of mass at the bottom is given by the desired expression. So that's how we derive this. And now we're going to analyze it. So a table showing the student's data is given below. What relationship can be graphed in order to yield a straight line whose slope can be used to determine the shape constant for the superball? So this is what shows up in every question, is what do you graph it, do it. So we were given that VCM is equal to square root 2gh divided by 1 plus beta. And again, when we do this, it's important that we identify our variables so we know what things should be graphed. So here, we changed h each trial, and we record the center of mass velocity at the bottom, because those are our two variables here. We could just graph v versus square root h right now and just be done with it, But again, the square roots are kind of not nice to deal with, so we just like to square both sides. And we can write this as v squared is equal to 2g divided by 1 plus beta times h. And I made my variables blue, so I can tell that this is going to be a y equals mx plus b situation. So then, after sending all your variables over to one side, we get v squared over h is equal to rise over run, which is equal to the slope, which is equal to 2g divided by 1 plus beta. So therefore, we can graph v squared versus h, get a straight line whose slope is given by the quantity 2g divided by 1 plus beta. So now we're going to add any necessary columns to the data table and graph our best fit linearization using that. So just moving over to the other one here. So we're graphing v squared versus h. I just have v. I don't have v squared, so I need to make a column where I square all of the v's. So through the magic of video editing, there's our v's. So we just squared them here. And I'll also move this over here now. So now we have our data. And we do actually have to figure out how to graph this ourselves here. So add any necessary columns and then graph your best fit. Well, we do know that this is v squared, well, v center of mass squared, in units of meters squared seconds squared. And then over here we have our h, which is just in meters. So we want to use at least like half the grid here. So I notice I can actually count by, I can actually sort of split this up every 4, and I can do my heights. So I can do 1, 2, 3, 4. I can make this 0 0.1. I can make this 0 0.2, 0 0.3, 0 0.4, and 0 0.5. Then for the V's, I'll use less of the grid here, but I can just actually count by ones. So this would be 1, 2, 3, 4, 5, 6, 7. All right, now we'll plot our points. So we have a point when h is 0.1, velocity is 1.21, so that's out here. Then 0.2, we get 2.56. It's about right here. Then for 0.3, we get 4 on the dot. Then for 0.4, we get 5.29. And you can see why they've kind of strayed away from asking us to actually plot the points, because it's a bit tedious. And then 5, we get 0.625. And now we just connect them with a best fit line. So again, when you're doing this, you're trying to get about half the points above, half the points below the dot, or sorry, below the line. And yeah, that's about good. So I actually get at least one of the data points to actually fall on the line here, which doesn't always happen. And now we did it. So calculate the slope of the best fit line and use that to actually get the shape constant. So we always have to get the slope. We'll do this by hand because sometimes you're not given the points and you have to estimate it just doing rise over run. So I know that this data point is on the line in purple. And I also know that, let's see, what's another good point here? This one also is on the line. So your data points are not guaranteed to be on the line. So I won't assume they are. So first we'll get the slope numerically. So slope as a number is just going to be equal to the change in y over the change in x. So my second y coordinate, it said, was 2.56. Minus, again, I picked that second point because it looks like it was about 1.5. And then divide by x2 minus x1. And well, my second point was at 0.2. Oh, and this is meters squared seconds squared. And then this is 0.125 meters. And after a quick cancellation of meters here, we do get an experimental value for our slope. We get, let's see, 2.56 minus 1.5 divided by 0.075. We get about roughly 14. And the units are meters per second squared. That's just how they work out. And then we also have the slope in terms of variables. So earlier we said that VCM squared was equal to 2g divided by 1 plus beta times h. So that also means that this expression right here next to the h is also our slope. So we also know that slope is equal to 2g over 1 plus beta. So therefore, we can just set up an equality here. So if we know that slope is equal to 2g divided by 1 plus beta, we can multiply both sides by 1 plus beta and get slope times 1 plus beta is equal to 2g. So we get 1 plus beta equals 2g divided by the slope, which means that beta is equal to 2g divided by the slope minus 1. And notice we can actually figure this out. So we can get 2 times 9.8 meters per second squared divided by the slope, which we found to be 14 meters per second squared, minus 1. And then from there, we just get 2 times 0.8. And we get beta is roughly equal to 0.4, which is 2 divided by 5. So notice that actually means that this super ball is actually pretty close to just being a regular old solid sphere, because 2/5 mr squared is the beta value for that. And then for just some error analysis to conclude with, the students find that when they actually measured the mass of the ball, they forgot to zero the scale, meaning the reported mass of the ball was too high. What effect, if any, would this error have on the slope of their best fit line? So again, do not just go with your gut instinct here. inform this result mathematically. Slope of the best fit line. That doesn't just spawn in from nowhere. So we actually had an expression for the slope of the best fit line up here. We said that the slope of the best fit line was equal to 2g divided by 1 plus beta. So, if they measured the mass to be too high, how would that affect the slope? Well, if there was an m up top here, making that m too high would make the slope too high. If there was an m in the denominator, that would mean that measuring the mass to be too high would cause the slope to be lower than it should. So this actually means that the student's experimental slope would actually be unaffected by this error, because slope equals 2g divided by 1 plus beta, which is independent of mass. So that's how we justify it. Again, if it did depend on it, you'd have to explain why that error actually occurs. So again, if there was a mass in the numerator, that would imply something like, well, measuring the mass would give us a higher slope than expected if the mass was too high, because they're proportional. But here, completely independent. So we do not need to include any of that. So yeah, again, this is way longer than any actual free response question. I just wanted to include all possible lab exercises that we could pretty much see in here. So everything from designing the experiment to the actual errors and the best fit, of course, solving for the quantity, and doing all that. The only thing that's missing, I guess, would be a y-intercept, which we could find examples of later.